Hi class. I wanted to add some information for you about conformal mapping and Laplace's equation. These things are in the notes, but I wanted to give you a short screencast to try to explain it a little more clearly so that I can be sure that everyone follows. And the basic point is the following. Suppose I start with a function phi, which is a function of two variables I'll call u and v, which is harmonic in these variables u and v. That is, it satisfies Laplace's equation, d squared phi by du squared plus d squared phi by dv squared equals 0. I'll call this combination del squared of u and v with respect to phi. Now, suppose u and v are themselves the real and imaginary parts of a separate analytic mapping f. So f of z, which is f of x plus iy, is u of x and y plus iv of x and y. So I'm going to view the u and the v inside this function phi as actually coming from the composition of first mapping from the xy plane to the uv plane and then evaluating phi at u and v. The point is that if phi of u and v is harmonic with respect to u and v, then when I view it as a function of x and y, where I view u as a function of x and y as I do here, and v as a function of x and y, this overall function phi of x and y is also analytic in x and y. That is, specifically in terms of equations, the del squared of uv of phi is equal to 0 by assumption. That's the assumption up here. Then this implies that del squared with respect to x and y of phi, where I take the x and y derivatives, is also equal to 0. So why is that? Well, there's two ways of viewing this. One is as the composition of two mappings. Basically, this mapping takes me from the xy plane to the uv plane. I can think of phi of u and v as the real part of a separate mapping, capital G, where there's an imaginary part psi. Since this is harmonic, I can construct an imaginary part psi such that the combination u plus I psi, where I view this as a function of u and v or as a function of u plus iv, this function g is analytic in the variable w, which is u plus iv. If I think of u plus iv, which is w, as instead coming from f, as I do up here, so w equals f of z, then you see that if I think of this as the composition of two functions, g acting on f, well, that's just, first I use the analytic function f to map from the z plane to the w plane, then I use the analytic function g to map from the w plane onto phi and psi. So the composition of the two, phi of x and y and I psi of x and y, is just the composition of two analytic functions. It should also be analytic with respect to z. And if that's analytic with respect to z, then it necessarily follows that it satisfies Laplace's equation in x and y. I wanted to give you an alternative derivation. It says this in the notes, but it doesn't give you a derivation. I just wanted to write it here, and I'll walk you through it, and these notes will be online if you want to see them. We can do it directly. Suppose we just say phi of u and v is phi of u of x and y and v of x and y. We can just use the chain rule for partial derivatives to compute the second derivatives of phi with respect to x and y. The first derivative is easy. The chain rule with respect to partial derivatives gives you d phi du times du dx plus d phi dv times dv dx. In detail, these partial derivatives here are taken with respect to y being held fixed. If I now take a second derivative, I'm going to write it in a somewhat strange way. I'm going to first take the derivative with respect to x. I'm going to use the product rule on these two terms. So the first term gives me a second derivative times what I had before. The second term gives me this times the second derivative of u with respect to x squared. And the same thing happens when I take the derivatives over here. First I get this mixed derivative on phi times dv dx, and then I get a term with respect to d squared v by dx squared. I can do the same thing with d phi dy, and I'm not going to say all of it, but it's here on the page. You can see I get a similar looking expression. If I now put everything together and I calculate d squared phi by dx squared plus d squared phi by dy squared, I get these terms here, but notice I've left out some terms because when I add them together, notice d phi du here is multiplied by d squared u by dy squared. D phi du here is multiplied by d squared u by dx squared, but the sum of d squared u by dx squared plus d squared u by dy squared is equal to 0 because u is harmonic, being the real part of an analytic function. Similarly, if I look at this term here, d squared v by dx squared, And actually, this was a typo, excuse me, let me fix that. That's actually a d squared v by dy squared. The sum of those two is also 0. So a bunch of terms cancel out when I add d squared phi by dx squared with d squared phi by dy squared. And I instead get this. Now, for each of these terms, for this term, this mixed partial derivative, I then use the chain rule. So let me walk you through one of these. I have to do this 1, 2, 3, 4 times. But if I look at this term, d squared phi by dx dy, dx du, I can write that as first I take d squared phi by du, which is d squared phi by du squared. That's this term. And then I get times du by dx. Then I get d squared phi by dv in du and dv by dx. That's just using the chain rule for partial derivatives to evaluate that. The whole thing is multiplied by du dx on the outside. I do this 3 more times. And when I do that, I get these additional terms. Now I can use the Cauchy-Riemann relations, and let me say take all these first derivatives here, for example, on these terms that are circled in blue. Let me write them all in terms of derivatives of u by using the Cauchy-Riemann relations, because ux is vy and uy is minus vx. When I do that, you'll see these two terms are the same, and these two terms are the opposite of those. They all multiply this mixed partial derivative. So when I add all of these together, I actually get an extremely simple result. I just get the Laplacian in terms of u and v, d squared phi by du squared plus d squared phi by dv squared, times this overall factor, du by dx squared plus dv by dy squared. So that is del squared with respect to x and y of phi is proportional to del squared with respect to u and v of phi. So that means that if this satisfies Laplace's equation in u and v, then phi satisfies Laplace's equation also with respect to x and y. And that's what we wanted to show. We wanted to show that if I started out with a function here, if I started out with a function which is which is harmonic in u and v, and I express each of these terms, u and v, in terms of the real and imaginary parts of an analytic function, then viewed as the function as a mapping from the original xy plane, it's still harmonic. Let me go through one example. There's another example in the notes, but let me go through one simple example where we can use this. Suppose we want to solve Laplace's equation in the xy plane, in the upper half plane. So here, subject to the boundary conditions that phi is positive phi 0 on the positive x-axis and negative phi 0 on the negative x-axis. Now, solving that in general is kind of complicated, but if I do a conformal mapping where I map from this z-plane, x and y, by using the log function, well, you notice the positive x-axis gets mapped. I'm going to define the logarithm, so the argument of z runs from 0 to 2 phi. So the argument of z along the x-axis is 0. So that means that log z, remember, is just log r plus I theta. It's the argument of theta. So the v component here is just the argument of z, and the u component is the logarithm of r. So along the positive x-axis, in the u plane, it maps onto the entire u-axis from negative infinity to positive infinity. Negative infinity corresponds to small values of x, positive infinity corresponds to large values of x, but the argument all along here, the v value is equal to 0. Whereas on this side, the v value is equal to pi. So up here, the potential is at minus phi 0 along the line v equals pi. So in the UV plane, what looked like a complicated physical situation is just a parallel plate capacitor, where I have the lower, the u-axis, the lower plate held at plus phi, on the upper plate held at minus phi 0. Well, it's pretty simple to solve that. We actually know what the potential is from a parallel plate capacitor. We know that the electric field lines are just uniform, and that means that the potential varies linearly, and the potential is a linear function which starts at plus phi 0 at v equals 0 and goes to minus phi 0 at v equals pi. So the phi of u and v is just phi 0 times 1 minus 2v over pi. So that's just the solution. We've solved this problem in the UV plane. We have to go backward, though. We have to get it in the xy plane. So remember, my mapping was log z, which is log r plus I theta. which is the log of the square root of x squared plus y squared plus I times the arctangent of y over z, where the branch of the arctangent is given such that the argument is between 0 and pi. Actually, sorry, here I can use, I can take minus pi over 2 to pi over 2 if I want, because all I really need to do is map the upper half plane correctly. So you see that u is the log of the square root of x squared plus y squared, and v is the arctangent of y over x. So viewed as a function of x and y, phi is phi 0 times 1 minus 2 pi times the arctangent of y over x. Now, this was a fairly simple solution in the UV plane. This is a lot harder to guess. And so this is the utility of conformal mapping. It allows you to transform Laplace's equation in one geometry into Laplace's equation in another. You see here that what corresponds to lines of constant potential are just radial lines because they have constant values of the arctangent of y over x. So I see here I probably should actually take this argument to be, well, I just have to take the argument to be consistent with that. So what you see here is the lines of constant phi are lines of constant theta, and the electric field lines are orthogonal to that. They go around in a circle like that. So there you go.